In this video, we're going to talk about Lewis structures. You may remember Lewis dot diagrams. If not, we're going to refresh our memories because we're going to need to use those. What Lewis structures do is they show us how the atoms in a covalent compound are hooked together. Remember that covalent compounds are compounds that are made from all nonmetals. And they are similar to Lewis dot diagrams because they involve those valence electrons. You want to follow a specific set of rules to get to the Lewis structure. Let me just tell you, do not shortcut this process because it is really easy to make a little mistake. So you want to make sure that you follow these rules. It's very straightforward and it's very easy to get the correct answer. But if you are kind of shortcutting, it's really easy to make a mistake. So let me give you the rules. The first rule is we're going to add up the number of valence electrons in a compound. Remember that we learned back a couple of units ago that group 1 and group 2 have 1 and 2 valence electrons respectively. The transition metals have 2, the F block elements have 2, group 13 elements have 3, 14 have 4, 15 have 5, and so on. So you can figure out by looking at the group number how many valence electrons a compound has. And we're going to add up the valence electrons for each of the atoms in the compound. We're going to guess at a structure and hook all the atoms together using single bonds. Remember we talked about the fact that a single bond is just a little straight line, and that's a shared pair of electrons. Usually the first element in the formula is in the middle, and usually the most metallic element is in the middle. And if you think about what might be more metallic, think about the way the periodic table goes. The nonmetals are to the right, the metals are to the left, the metalloids are on the stair-step line touching on a side. Things that are more left would be more metallic. We want to give all of the atoms on the outside of the structure an octet. Remember that a full octet is 8 valence electrons so that it's stable. And I'll show you how to do that. I know it sounds kind of crazy right now, but let's finish the rules. If you have any electrons left over after that step, we're going to add all of them to the central atom. If you don't have enough electrons to give the central atom a full octet, the first thing we're going to do is check for a deficient atom. Those are beryllium, boron, and aluminum, and we'll talk about what a deficient atom is. You'll need to know these, so make sure you memorize them. Then you want to try a double bond, one double bond. If that doesn't work, we'll talk about how to move forward. Then you can also try a triple bond. You'll want to leave a gap in your notes for some hints. We're going to come back and put them in. I would leave at least 7 or 8 lines because there are several. So let's take a look at our first one. So we're going to start with carbon tetrachloride. Hopefully you recognize the formula for that. It's CCl4. So let's start with carbon tetrachloride. Think about the formula. I expect you to know the formulas now. That's CCl4. Let's go ahead and follow the rules, and then we'll draw our Lewis structure. So let's start by adding up the valence electrons in our compound. We've got 1 carbon atom, and that each carbon atom has each carbon atom has 4 valence electrons. It's in group 14. So we've got a total of 4 valence electrons from that 1 carbon atom. And then we have 4 chlorine atoms, and that's in group 17, so it has 7 valence electrons. So a total of 28 from those 4 carbon atoms. Now when we add those up, we get a total of 32 electrons. The next rule says that we're going to guess at a structure and hook the atoms together using single bonds. And it says usually the atom that is the first element is in the middle, so that's carbon, or the most metallic, which carbon would be because it's further left in the periodic table than chlorine. So let's put carbon in the middle. and we're going to hook on those chlorine atoms with single bonds. Now remember that each single bond counts for 2 electrons, so we need to keep track of our electrons. So 2, 4, 6, 8. And we're going to subtract that from our total so we can keep a little running tally. It's going to be important so we can make sure we did it correctly. The next thing we need to do is give each of the atoms on the outside a full octet. Remember that an octet means 8 electrons. This bond, this shared pair, counts as 2, so we need 6. So 1, 2, 3, 4, 5, 6. So just draw them on the 3 other sides, if you think of that little imaginary box around each atom. These can get a bit tedious, but you want to make sure that you follow the rules because it will help you keep from making a mistake. So let's add up our electrons that we've used. We've got 6 around each of the 4 chlorine atoms. That means we've used 24. So we have no valence electrons left. We still want to think about the rules. If we have any electrons left over, we would put them on the central atom, but we don't. So we want to check for a full octet on that central atom. Remember, our central atom here is carbon, and then these outside atoms are the chlorines. So carbon has 2, 4, 6, 8, which is a full octet. So this is the last rule, super secret, but make sure that you do it. Check for the fact that you have used all of the electrons, and check to make sure that each atom has a full octet. So 4 bonds on the central atom, which gives us a total of 8. Then on each of the chlorines, you've got a bond, which is 2, plus 6 more, which is a total of 8. So we've got a full octet on each of the atoms, and we've used all of our valence electrons. This is the correct Lewis structure. Let me go ahead and give you the hint to put in your notes. Carbon is almost always going to be in the middle when carbon is in a compound, and that's because of the way that it bonds. All right, let's try another one. All right, ammonia. You should know the formula for this. That was one of the covalent compounds you were supposed to memorize. Ammonia is NH3. So let's go ahead and try the Lewis structure for ammonia. So we know that we know that one nitrogen atom has 5 valence electrons. And we know that we have 3 hydrogen atoms that each have 1 valence electron. So that's a total of 3 from the hydrogen and a total of 8 for the compound. So let's go ahead and draw our structure. Nitrogen is going to be the one that goes in the middle. And we're going to hook each hydrogen atom to it with a single bond. Now we've used 2, 4, 6. Remember, each bond counts as 2. It's a shared pair of electrons. And we've got 2 left. All right, so what we need to do is look to see whether our outside atoms have a full octet. Now here's the thing about hydrogen. Hydrogen is in that first row. That 1s subshell is all that it has. Remember that that s subshell only holds 2 electrons. Hydrogen only has to have 2 electrons to get an octet. You can see me making the little funny quotes. So the hydrogen doesn't actually have to have 8 electrons to have a full octet. 2 electrons gives it a full subshell, which gives it the same stability as 8 electrons do for the other elements. So looking at that, hydrogen has a full octet. And so we're going to look at our next rule, which says if you've got any electrons left over, you're going to put them on the central atom. So we're going to use those 2. We want to subtract, and that leaves us with none. And now what we want to do is make sure we have a full octet on our central atom, so 2, 4, 6 from the bond and 2 from the leftovers after we gave all the outside atoms that full octet, which means that nitrogen has a full octet. Hydrogen, each of the hydrogens also has a full octet, so remember that check. Make sure all the atoms have a full octet, and we have used all of our valence electrons, okay? If that's the case, then this should be the correct Lewis structure, and it is. Let's check for our hint. So here you want to write down that hydrogen only needs 2 electrons to get an octet. Let's try another one. Sulfur hexafluoride, you should know the formula for this, SF6. So let's go ahead and add up the valence electrons there. We've got sulfur. There is 1 sulfur in our formula, 1 sulfur atom, and it has 6 valence electrons. And then fluorine, there are 6 of those. And each one, because it's in group 17, has 7 valence electrons, so that's 42. So a total of 48 valence electrons for our compound. Now let's go ahead and pick the central atom. Sulfur is more metallic than fluorine, plus it's written first, so we're going to go ahead and write that. So S, and then we're going to hook everything else to it with a single bond. So 1, 2, 3, 4, 5, 6 fluorines. Now you're probably going, wait a minute, how are we getting all those fluorines on there? We'll talk about that in a minute. Look at how many electrons we've used in the bonds. Remember, we've got 2 in each bond, so a total of 6 bonds, which is 12 electrons. And that leaves us with 36. And then we need to give each of the outside atoms a full octet. So fluorine has 2 in that shared pair, so we're going to have to add 6. To each of those fluorines. Now if we've used 6 electrons on each of those fluorines, then we know that 6 times 6 is 36. So we're going to subtract that from our total electrons, and that leaves us with no electrons. So what we want to do now is we don't have any extras to put on the central atom, so we want to check that central atom for a full octet. Well, clearly sulfur has more than a full octet, because an octet would be 4 pairs or 8 electrons. Here, sulfur bonds with 12 electrons, so 6 atoms. And that's okay in this case. Remember that chemistry has lots of exceptions. So we've used all of our electrons. Our outside atoms each have a full octet. We want to check that. And then our central atom actually has a full octet plus some. This is the correct Lewis structure for sulfur hexafluoride. Let me give you the hint. Some central atoms can have more than an octet of electrons. Sulfur and phosphorus do this. And if you look under sulfur and phosphorus, there's arsenic and selenium. There's like a little box. Those are the ones that you will tend to see in this class. So just be aware, if I give you a compound and I have 5 or 6 things hooked to it, that's okay. If there are 5 or 6 atoms that are going to hook to that central atom, that's okay. I'm not trying to trick you. All right, let's try another one. Boron trihydride, you should know the formula for this. BH3. So let's go ahead and add up those valence electrons. So boron there's 1 atom of boron and it has 3 valence electrons. And then hydrogen, there are 3 hydrogens and they each have 1 electron. So if I total all those electrons up, I get a total of 6. I know you're thinking, great, not so many dots to draw. So let's go ahead and do this. Boron's going to be in the center. We're going to hook our hydrogens onto that central atom. Now remember, we want to subtract our electrons that we've used. We've got 3 bonds, 2 each, so that's a total of 6. So that leaves us with no electrons. If we had extras, we'd put them on our central atom, but we don't. So let's look at this. Now, do our outside atoms each have a full octet? Remember that for hydrogen they do. They only take 2 electrons to have a full octet. Now the other question is, does boron have a full octet? It doesn't have a full octet, but this is one of our exceptions. Boron can't have an octet. Boron is what is called a deficient atom, and you'll need to know the 3 deficient atoms, boron, beryllium, and aluminum. They are atoms that can have less than a full octet and still be the correct Lewis structure. So you want to make sure that that you know those for the test and the quizzes. So here we have no valence electrons left. Each of our outside atom has a full octet. Boron does not have a full octet, but because it's a deficient atom, that's okay. So let's go ahead and look at our hint. That's the correct Lewis structure. So boron can't have an octet. Boron, beryllium, and aluminum, because they are deficient atoms, very rarely have an octet of electrons. See if you can figure out why hydrogen can't be a central atom. All right, let's try another one. Okay, so formaldehyde, I have to give you the formula for that one. I don't expect you to know it. This is a compound. I'd like you to try to think up a structure for it. So pause the video, see if you can figure out how these might be hooked together. Let's go ahead and add up the valence electrons here. We've got 1 carbon atom with 4 valence electrons. That gives us a total of 4 there. 2 hydrogens, and that gives me a total of 2. And then oxygen has 6 valence electrons, 1 atom of that. So when we add that up, we get 12. Pause the video and see if you can figure out the structure for this compound. Okay, so let's look at some possibilities here. So often I will see this. Sometimes I will see this. Sometimes I will see this. Sometimes I will see this. So which structure is correct? There are lots of different ways you can kind of hook these different atoms together. Remember to try to think of the fact that it's going to have a central atom. If you look at these 2 structures, one thing you have to think about is that hydrogen, it can only form 1 bond because it only has that 1s subshell with electrons in it. So it has 1 and it shares that, and it shares it with an atom that can give it 1. It doesn't bond with more than 1 element. It only forms 1 bond. So these 2 are not correct. The other thing that we have to think about with these ones is that Mother Nature likes symmetry. So if you know what symmetry is, it's when things are equal on both sides, like your hands or your eyes. And if you look, this structure is symmetrical. You can actually draw like a little dotted line through the center here and see that that is the same on both halves. It's like looking in a mirror if you did that. So this one would not be the best structure, okay? So let me get rid of those, and let's draw this structure for formaldehyde. So looking at this, we've got 1, 2, 3 bonds, so we've used 6 electrons. and we have 6 left. So let's go ahead and check for a full octet on our outside atoms. Hydrogen, each of those hydrogens has 2 in the bond, that's all it needs. Oxygen has 2 in the bond, but it needs 6 more to get a full octet, so we're going to put all 6 electrons there. And that gives us a total of 6. We've used all our valence electrons, so let's go ahead and do our check. Do all of our outside atoms have a full octet? Yes. Does our central atom have a full octet? No. And this is the step that a lot of people will skip. Do not skip the step. So the central atom does not have a full octet, so we are going to have to do something else. Let's check for a deficient atom. Carbon, not a deficient atom. So what we're going to have to do is try a double bond. Okay, so just let's mark through this. Let's start again here with 12 electrons. We don't have to do all the math again. And then let's set up another structure. So think about where we might try a double bond. We know that hydrogen can only form one bond. So hydrogen is not going to get the double bond. The double bond goes on oxygen. Now, 2, 4, 6, 8, we've used a total of 8 electrons. Remember that double bond is 2 shared pairs. And that leaves us with 4. And each of our hydrogens has that full octet, so we're going to put the other 2 pairs of valence electrons here on oxygen. Now, we've used all of our electrons, so let's check. Each of our hydrogens has a full octet. Oxygen has 2, 4, 6, 8, so it has a full octet. Let's check carbon. 1, 2, 3, 4 bonds. Carbon has a full octet. So now we know that that's the correct Lewis structure. Do not forget to check. Don't assume that because you've used all of the electrons that you've got the correct Lewis structure. Double check for that full octet on your central atom. Let me give you a hint. We want to think about which structure is correct. Usually the most symmetric structure will be the correct one. Hydrogen cyanide, HCN. You've probably heard of that before. It's very poisonous. Let's go ahead and add up our valence electrons so we know that hydrogen we've got 1 atom and it has 1 valence electron, so a total of 1. And hopefully you're doing this right now. I might suggest that you would pause the video at this point and try to add up those valence electrons on your own. You should have your reference table in front of you, and that way you can go ahead and make sure that you are getting the hang of doing this. All right, so a total of 10 valence electrons for hydrogen cyanide. Now, central atom, hydrogen, carbon, or nitrogen. Now remember, hydrogen is not very metallic. It's just over on the left side of the periodic table because it has that 1 valence electron, so we put it in group 1. Carbon is usually the central atom, so let's put that there. And then we're going to attach the other 2 to it. So we've used 4 electrons in our bond. That leaves us with 6. Hydrogen has a full, we're going to check for a full octet on the outside atoms. Hydrogen has a full octet because it has 2 in the bond. Nitrogen has 2 in the bond, but it needs 6 more to have a full octet. So we've used all of our valence electrons. Our next step is to check for a full octet on our central atom. It does not have a full octet. It only has 2 bonds, which are 4 electrons, so no octet. Carbon is not a deficient atom, so we're going to have to try again. So let's cross that out. Don't worry about marking things out on your paper. So let's start with 10 electrons again. We're going to put carbon in the middle. Now, carbon's not a deficient atom, so our next step is to try a double bond. Remember that hydrogen will only form 1 bond, so we need to put our double bond on nitrogen. So 2, 4, 6 electrons in the bonds. Subtract those, we've got 4 left. All right, so hydrogen has a full octet. Nitrogen gets those 4 electrons to give it a full octet. Okay, so as you can see, hydrogen and nitrogen have a full octet, but carbon does not. So what we want to do here is try the next step. Now, this is where you have to think, okay, I can either try another double bond or a triple bond. You always want to start by just trying one. Remember that hydrogen can only form one bond, so we know that we are not going to try another double bond, so we are actually going to try a triple bond. I'm going to do the electron math over here, and we're going to give carbon and nitrogen that triple bond. Now we have used 8 electrons. Remember that each of those lines is a pair, so that counts as a triple bond, counts as 6, plus 2 is 8. We have 2 left. We're going to put those on nitrogen. Subtract that from our total. That leaves us with none. Hydrogen has a full octet. Nitrogen has a full octet, 2 in the pair and then 6 in the bonds. And then carbon has 1, 2, 3, 4 bonds, which is a full octet. This is the correct Lewis structure. I will tell you that you will want to be sure that you are following the rules and not trying to erase. I would just suggest crossing those structures out, because it's very easy to make a mistake when you're erasing and adding bonds and electrons. This will help you make sure that you do it correctly. It just takes a little more space. I know you don't like messy papers, but it's important to help you make sure that you keep track of everything. All right, let's try another one. The nitrate ion. So where would you find the formula for the nitrate ion? Hopefully your head is saying, the yellow packet. Okay, so the nitrate ion is NO3 with a 1- charge. So let's go ahead and do our electron math here. We know that we've got 1 nitrogen atom with 5 valence electrons. And then we've got 3 oxygen atoms, and each of those has 6 valence electrons. So we've got a total of 23 electrons. Now, looking at that number, what seems unusual about it compared to what we've already done? Hopefully you're thinking, that's the first time I've seen an odd number for my total of electrons. And that's important. Remember, we're always dealing in pairs of electrons, so we need to think about that. If you come up with an odd number of electrons, either check your math or check and see if your atom or your ion has a charge. Because if there is a charge, we have to take that into account. So think about it. If it has a negative charge, it has 1 extra electron. And to take that into account here, we need to add that up to our total, which gives us a total of 24 valence electrons. So let's do our structure. Nitrogen's going to go in the center. We're going to hook 3 oxygens to it. That's a total of 6 electrons. That leaves us with 18. We're going to give each of our outside atoms a full octet. They each have 2 in the bond, so they get a total of 6 more. And when we add those up, there are 3 oxygen atoms with a total of 6 electrons each, so we're going to subtract our 18 electrons. We've used all of our electrons, so we want to check for a full octet on our central atom. It does not have one, so this cannot be the correct structure. Nitrogen is not a deficient atom. So that means we need to do what? Hopefully you're saying try a double bond. So let's start here again. Remember that we like symmetry in nature, so I'm going to put that double bond on the central oxygen there. So we're starting with 24 electrons again. We don't need to show that top part. And we've now used 8 in the bond. We've got 4 bonds total, and that leaves us with 16 electrons. Each of these 2 oxygen atoms has 2 electrons in the bond, so we're going to give each of those 6 for a total of 12. And then we need to give this oxygen 4. It's got 4 in bonds and it needs 4 more. So 12 from these 2 oxygens plus 4, that gives us 16 electrons. We've used all our valence electrons. Each of our outside atoms has a full octet. Now our central atom has a full octet. So we know that that is the correct Lewis structure, except for ions, we want to show that additional electron. So you're going to draw a big set of square brackets around the outside, and then you're going to put the charge to show that that is an ion that has gained or lost electrons. There's another practice set that you can look at that will give you the opportunity to look at some additional practice problems. So take a look at those.